As procedural programming became more and more mainstream, computer scientists started to notice the issues behind states and side effects. Some languages offered a complete paradigm shift, completely abandoning the notion of state. This exodus formed the alternative paradigm family, declarative paradigm. Other languages, however, went on a different direction. These languages offered a solution to fixing state by introducing richer features and an intuitive design. From this approach, the paradigm object oriented programming was born. This programming language right here, called Simula, was credited to be the first object oriented programming languages. Its rich syntax on simulation of real world objects and real world mechanisms was the father and the originator of the object oriented concepts that you know today. So, as time went by and as technology evolved, computer scientists noticed new issues on the code that they were writing. The goal of building the most optimized machine code became less and less of a priority. Programmers had under their disposal faster and better hardware. As the demand for complex systems grew, the priority shifted from code that runs to code that was intuitive. As programmers started to build bigger and bigger systems, they started to notice the issues in terms of maintainability. This shift on focus can be seen from the extremes of procedural programming, such as the programming language assembly. Assembly code was not really built to be intuitive, it was built to reliably work. Assembly contained mechanisms to move data around and to control program flow. These features were enough for that time since the objective of programming was to write efficient code that bulky, slow computers or CPUs understand. Assembly programmers did not have the time to worry about code elegance or intuitiveness. But the landscape started to change when hardware started becoming better and software started becoming more complex. Speed and memory wasn't that much of an issue anymore, so computer scientists' focus shifted towards the issue of maintainability. Software became bigger and more complex, and understanding other programmers' code became more and more difficult. In fact, understanding your own code was also becoming difficult. If you write a piece of code for some system 3 years ago and you try to read what this piece of code means, you might have a hard time understanding what this assembly code would mean. In fact, because of this, writing code that a computer understands isn't enough anymore. A good programmer must write code that humans understand as well. Code shifted from human centered to human from computer centered to human centered. But instead of redesigning the concept of imperative paradigm to solve this known issue of maintainability, object oriented programming sought to build on top of the features of imperative programming. That is why we can think of the OOP paradigm as a successor to the imperative programming language. State, despite its known issues, still exists, but OOP gave imperative programmers extra tools to protect code from being carelessly mutated. Because of this, OOP stayed under the imperative family since the programmer is still focused on telling the computer what to do using assignment statements and mutations. So here we're going to talk about the fundamental concepts of OOP. We're going to talk about them in detail in future lessons, but let's introduce them for now. Object-oriented programming is usually defined using its three core design principles: encapsulation, inheritance, and polymorphisms. It is said that any programming language that contains these mechanisms is an object-oriented programming language, but Actually, calling the entirety of a programming language OOP can be problematic since you are indeed free to write code written in an quote unquote OOP language without actually using these design principles. Because at the end of the day, OOP is not merely a language classification, but it is a paradigm. It is a set of ideas. Some programming languages are indeed intentionally written to be used for OOP design, but these classifications are less important than judging if the code itself, written by the programmer, adheres to OOP's design principles. Let's start with the star, the building blocks of object oriented programming. What exactly is an object? So, an object is a living organism in your code. To grasp the capabilities and limitations of an object, people sometimes try to anthropomorphize objects. They try to give it some kind of life, treat objects as organisms. Treating objects as organisms will guide you on how you use objects effectively. Just like any creature, an object has both form, which corresponds to the attributes or sometimes called fields, and behavior, called methods. This is one of the reasons why C's struct concept or construct is not an object since structs only have form, they don't have an attached behavior. Objects, written to be representations of real world nouns such as a person or an employee or a file. The best way to design objects is to simulate the real world form and behavior of what these objects represent. You can think of objects as the representatives of things in your code. Since you cannot shove an entire actual employee in your system, for example, you can instead create a representative of that employee using some employee object. If you start thinking about objects like representatives instead of mere data holders, you'll be able to design a safe and elegant object. Let's move on to the class. Often discussed alongside an object is the class, and there's usually a lot of confusion when identifying the difference between a class and an object. And it is probably because in the universe of your code, the class and the object will have the same name. But they are actually quite different. A class is the specifications for the creation of objects. If you want to give a class a more proactive role, you can think of the class as the factory that builds objects. There are a lot of analogies out there to illustrate the relationships of classes and objects. For example, if you think of a star shaped cookie cutter as a class, then these star shaped cookie cutters make star shaped cookies themselves, which represent your objects. And if ever you want to make star shaped cookies, you use the star shaped cookie cutters. You can also call objects as instances of a class. In fact, that's what I call objects most of the time. So, whenever you see me discuss something and I mention instances of a specific class, for example, I always mean its objects. That's the my favorite way of addressing an object, an instance. And for example, the cash class, for example, the literal amount $2.75, for example, is an instance of that cash object. Or a cat named Garfield, for instance, is an instance of the class called mammal. If an object is a representation of a tangible real world object, then the class is the conceptual type slash category of the real world object. The following class diagrams are the representations of book and employee. These the attributes of the book are title, author, published date, pages, and here are the types of each of these attributes right here. These attributes also simulate the form of a real world book in the same way that a book has some kind of title, it has some kind of author, it has a published date, and it has pages. Then, to properly simulate what a book's form looks like, then it must have these attributes or fields as well. The object also has methods called ISBN and numPages, for example. And these methods also simulate how an object behaves. And a book in particular doesn't really have a lot of behavior. You can sort of look at the book and check how many pages there are. And this is reflected or simulated by this behavior right here, this builder function called numPages. Another is to check what is the ISBN of that book. And this is generated using this ISBN function right here. On the other hand, the attributes of an employee are also representatives of its attributes in real life. It has a name, which is a string, and it has a salary and a job title as well. And it has a specific behavior right here that allows the employee to be manipulated by reassigning it to a specific job. So don't worry if you have some confusion understanding what this diagram means right here. There's a dedicated discussion on understanding this one. This is called Unified Modeling Language, specifically for class diagrams. And you will encounter a lot of these in this course because I try my best not to show specific code as examples since I'm not really teaching specific programming languages. I'm teaching the paradigm itself. So the following are representations of whatever these classes are. So book, for example, instances of books may look like these. So one instance of a book, for example, would be called Book 1, and its title would be this one, Corpus Hermeticum. The author is Hermes Trismegistus, for example. The published date is this following date right here. Another instance of a book, for example, would be this book right here, Behold, a Pale Horse. The author is Milton William Cooper, some conspiracy theorist who killed someone. A representation or an instance of the employee class right here would be this employee called Rubilito Abelia right here with a job title of Instructor 1. So before we play around with some code, let's dive deep into the philosophy of the object-oriented paradigm itself. The base premise of OOP is a concept called data hiding. And this formal OOP term describes what I mean when I say that what OOP did for imperative programming was to allow the programmer to create artificial boundaries between irrelevant data and behavior. This specific concept right here is what elevated imperative programming to be the pragmatic and ubiquitously useful paradigm, which is OOP today. This is what OOP added on top of imperative programming to solve the issues of state, to solve the issues of careless mutation. In the eyes of OOP design, procedural code is a mix of data and functions arbitrarily tossed in a spaghetti of mutations and side effects. And OOP's mechanism to create these boundaries in the form of objects brought structure to imperative programming. All the attributes of a book object doesn't need to be accessed by the methods of a library card object. That's because in the real world, a library card doesn't need to know what's written in page 69 of some book, for example. Some data in book should be hidden from a client class called library card. Object-oriented programming's obsession to simulate real-world objects is not caused by its dream to become an exact representation of the real world. Object-oriented programming obsesses over structure and simulation because it is a necessity for human comprehension and therefore maintainability. Systems need good structure not because well-structured code is pleasant and elegant to look at, but because our feeble minds can't process poor structure efficiently. In fact, the reason why we call a well-structured piece of code as elegant is because our tiny limited minds are able to process it. This process of modeling elegant object representations is basically determining what the public interface of that object may be. This is another important concept of OOP. The interface of an object is sort of the set of attributes and methods. Methods, by the way, are what we call functions inside a class. Anyway, you will see what all of these look like in code. But for now, let's talk about its philosophy. So the interface of an object is the set of attributes and methods that other objects can use to interact with it. The attributes and method that are not in the interface is essentially hidden information inaccessible from the client objects. For example, given a book object that interacts with a library card object, the library card object's interface to interact with a book may only contain title and author. Because this is all the information it needs to properly do its job. You can even hide those attributes and let the library card only interact with book using a borrow method which lists the books as borrowed in the library card. It doesn't need access to the attributes of the book to do this. It interacts with the book itself as a whole. And you're going to see a lot of these relationships in object-oriented programming. And this small interaction right here is already a good example of good object-oriented design. The way a client, an object that is dependent on a specific other instance, for example, like a book, does not necessarily interact with it like a book. Its interaction is abstracted through this interface right here. And it doesn't even need to be aware that what is interacting with is this specific book. It only needs to be aware that it is interacting with a conceptual borrowable item. And in its eyes, the only useful information, the only relevant methods that it needs are the following: how it is able to see the unique item ID for clerical purposes, for example, what the common name of this book may be so that it is able to display it in the library card when written down. So these are the only attributes and methods that are relevant for library card. Therefore, these are the only attributes and methods that are available for access. Again, don't worry if this diagram is a little bit confusing. This is another example of a class diagram written in UML. And we're going to dive deep into how to understand and write your own UML. And speaking of this interaction right here, creating interfaces like these provide OOP with the mechanism to create abstractions in the object level. The term abstraction is actually quite overloaded in OOP and computer science in general. The abstraction that I'm talking about in this context is the concept of abstraction itself, not the specific abstraction relationship between objects. But they are related, so it's not really a loss if you confuse one over the other. So creating interfaces like these provide OOP with the mechanism to create abstractions in the object level. An abstraction in computer science in general is basically a model of computation that is free from its implementation. The concept of abstraction is not necessarily an OOP thing, because in the same way that functional programming creates abstractions of mathematical functions by writing lambdas without side effects, OOP creates abstractions of objects using interfaces that don't specify the exact implementation of an object. In the example above, the interface, or in the example that I showed you a while ago, the interface borrowable item is an abstract representation of something from the library that can be borrowed. So this abstraction right here, and one of the reasons why I really love this example is because a borrowable item is not really something that has a conceptual form and behavior. Borrowable item is just an abstract representation of something from the library that you can borrow. I mean, if you imagine what this looks like, or you imagine how this behaves, you might imagine a book, for example, but it's not necessarily a book. It could be other things in the library that you can borrow. An interface like this, borrowable item, contains method names and type signature, but when you look at the contents of the code written for borrowable item, you'll notice that it doesn't actually contain any code. That is because a borrowable item is an abstract representation. We are not supposed to care about the implementation of the method's unique item ID and common name if your library card and you're interacting with borrowable item. You shouldn't care about the exact way it is implemented. You shouldn't care about the exact contents of its code. What you should care about is that unique item ID should return a specific type, which in this case is an integer, and common name is something that returns an integer. And you should also be concerned about how you would apply or how you would invoke these methods as library card. How do you use unique item ID? Do you have to pass these do you have to pass these parameters? So in this case, you don't pass any parameters here. But those are the only things that you need to be concerned about as a library card. The client itself, to be able to properly borrow a borrowable item, it only needs information on how to invoke unique item ID, meaning it's a relationship with borrowable item, and by extension, its relationship with book is how it is able to interact with it through the interface and through the methods that are defined, or not exactly defined, but specified in the contents of borrowable item. So the reason why this structure still works is because we have a concrete class called book, which is what we call a realization or an implementation of borrowable item. A book is something from the library that can be borrowed. So in this specific example right here, we can think of book as a realization of borrowable item. You can think of book as something that can be borrowed from the library card using the library card. Because a book is a borrowable item, it must also behave based on the specifications of a borrowable item, meaning it must contain the methods unique item ID and common name as well. Meaning these unique item ID and common name would be implemented inside the contents of the class book. And this is how you define the behavior of a book. How do you define the common name right here? Is the common name of a book its title, for example? Is the unique item ID of a book this book ID, for example? So it might be a little bit confusing to understand this specific concept without actually trying it firsthand. And don't worry, we will dedicate a specific lesson for actually doing this hands-on. This is just a little bit of introduction. So you might wonder though, why even go through all of this trouble? So you might think, if something from the library that can be borrowed is an abstract idea, what is the point of modeling its representation? This looks like some extra code lang just to represent something that doesn't really have an exact form in the real world. And For the current structure we created, this does feel like extra code because our system is small enough right now. But if you imagine as your system grows and you need to incorporate other things from the library that are not books but can be borrowed, for example, a library also contains periodicals. For example, it contains iMacs that you can borrow as well. Periodicals like newspapers or magazines, or I'm not sure, whatever you can go borrow in the library. So you need a different representation for a periodical. You cannot use the representation book because a periodical has different things. It doesn't really have a published date. It has, on the other hand, it has more of like an issue number, for example. It doesn't really have a specific title. It has the title of a periodical and it has the title of the specific issue, for example. So periodicals and books have a bit similar forms, but they are actually different. And if you compare that with another borrowable item, which is an iMac, for example. So an iMac, for example, is something that can also be borrowed from the library, but the form and the behavior of an iMac is way, way different compared to a book. And since these uh, representations, periodicals, and books are also something that the library that can be borrowed, these must also be realizations of a borrowable item as well. And since we've already established this interface right here as sort of the middleman that interacts with library card, you only need a tiny effort of writing the implementations of each of these, of this lang the I. This periodical right here, and in the future, maybe an iMac, for example. With that tiny effort of writing implementation, including the realized methods for unique item ID and common name, we added an extra interaction that automatically allows library card to borrow these other borrowable items as well. And it doesn't even know that there are new types of borrowable items. It doesn't even know which exact type of borrowable item it is borrowing. It doesn't even know that something has changed in your system. So you can think of all of these extra code that you write as investments, that you write this extra amount of code right now so that in the future you don't have to write more code. We will discuss this specific relationship in detail, this realization relationship that you see represented in UML as this arrow right here, and other relationships as well in a future dedicated lesson. So moving on to the philosophy of object-oriented programming, let's summarize what we learned so far by discussing how these capabilities characterize the philosophy of OOP. The paradigm aims to solve the issues of state and maintainability by allowing programmers to create boundaries between its mix of attributes and methods. And I'm not going to be tired saying this because I'm going to be saying this again and again. This is the specific feature that object oriented programming added to procedural programming and imperative programming in general, the ability to erect or to create these boundaries between all of the disembodied attributes, disembodied variables, disembodied functions. It is able to gather all of them into a specific fact, into a specific concept. And that concept is the object structure that you create. A library card's name, for example, shouldn't be mixed with the book title, for example. So we put a boundary between them by encapsulating them into their own respective objects. You can imagine these objects as amorphous blobs with surface separating the methods and attributes inside it from other things in your code. These amorphous blobs, for example, let me draw what they are represented in my mind. They have some form of volume and surface, for example. And these volume and surface represent uh, the code that you write. The volume of this formless blobs represent the code that you write for implementation, while the surface right here represents the code that you write as its interface. The interaction between two objects is characterized by the surface of the objects, not its implementation. Another amorphous blob, for example, is able to interact with this other amorphous blob based on how the surface looks like. This other one, for example, will interact with this other one based on how its surface looks like again, not the volume or the core of these blobs. The volume of the object here shouldn't dictate how the objects relate to each other. In fact, everything inside the object should be inaccessible to other objects as well. The private, hidden things that you have written in the implementation shouldn't be revealed to this other object right here. It shouldn't be privy of what this exact behavior, what the exact attributes of this specific object right here. Objects should only see each other through the surface. This means that the interaction between objects should be defined by this surface or this interface. In the same way that you interact with your television, for example, using the physical buttons in your remote or even the physical buttons found in your TV, you interact with your TV that way. You don't interact with your TV by opening it up and messing with its circuitry. The way you interact with the world around you, for example, you don't uh, take in oxygen, for example, and individually place them, distribute them on your cells. What you do is you interact with it through the interface of your senses, through the interface of your nose and your mouth, for example. That is your boundaries between the world, and these boundaries are at the same time the definitions of how you interact and how you relate with your surroundings. And your job as an OOP programmer is to make sure that the complexity of the surface grows slower than the complexity of the core. The complexity of the implementation or the surface shouldn't change as your system evolves. As your system changes, as your system grows, all of the edits, all of the updates, all of the changes, all of the manipulations that happen inside the core or the volume of these blobs of these objects, as much as possible, this hidden implementation shouldn't affect the surface or the interactions between each objects. This is what harmony and elegance in OOP means. When objects interact with each other seamlessly and intuitively, regardless of what their insides look like. And that is all for this discussion.